Hello everyone. Today we're going to learn about backtracking. Backtracking is a very powerful algorithm where we're going to leverage the true power of the computer to solve problems. Everything we have learned so far has been a good preparation when we come to backtracking. Backtracking is built upon a lot of knowledge that we have learned, and we're going to put them together to truly understand how we can leverage the power of the computer to solve challenging problems. This tutorial is a part of the Data Structures and Algorithms class. First, we're going to have a look at typical problems solved by backtracking. It's virtually any problem. That is how powerful backtracking is. Although it sounds very powerful, backtracking is actually a very simple algorithm. Backtracking is a smart brute force solution. It uses depth of search to branch out and list all possible solutions, and it uses bounding conditions, the conditions given by the problem statement, to stop the unnecessary branching for better performance. And that's all what backtracking does. It's a smart brute force solution, uses DFS to branch out, and bounding conditions to stop the unnecessary branching for a better performance. Usually simple brute force solution gonna give exponential or factorial time complexity, but with backtracking, it's smart and it uses bounding condition to stop the unnecessary branching. So usually backtracking gonna bring down the time complexity to polynomial time. Again, backtracking is really simple. It's depth of search plus bounding condition. To learn more about it, let's have a look at our example. Our example problem is n queens. We are given an n by n matrix. In our case here, n equal to 4, and we are tasked to place n queens into our board. In our case here, it's gonna be 4 queens. And the condition for all the queens placements is they cannot attack each other, just like in chess. They cannot be on the same row, they cannot be on the same column, and they cannot be on the same diagonal. Let's try a queen placement here at position 0, 0. On this board, we only have one queen, and by placing the queen on 0, 0, immediately we cannot place any queen on row 0 and column 0. And also on the diagonal. Basically, it's all the places in red with the red cross here. That is because of the condition of the problem statement that the queens cannot attack each other. They cannot be on the same row, they cannot be on the same column, and they cannot be on the same diagonal. So for placing the second queen, we only have 6 choices left. They are the cells in white here. For our second move, we place another queen as the position of 1, 3. And by placing the queen at 1, 3, because of the bounding condition, the new queen at 1, 3 has eliminated more cells, which are the cell in black with the red cross. So for the next queen placement, we only have 2 choices. They are the cells in white here. Cell 2, 1 and cell 3, 2. And from here we know that we cannot have a successful queen setup for all of the 4 queens. Because if we place the next queen, the rule of no queen on same diagonal, we're gonna eliminate the other cell. And then we have no place to place the 4th queen. And then we need to try another setup. Maybe moving the first queen placement from 0, 0 to 0, 1. And then we're gonna try again with the same strategy. For a problem like this, where there are so many possibilities to make a move, and choosing the next move, which is the next queen placement, depend on what we did on the previous move, and we don't really have any logical inference from the problem statement to choose the next move. We only have the elimination conditions, like this condition that queen cannot attack each other here. When we face problems like this, backtracking is an excellent algorithm to solve this kind of problem. And the way backtracking solves this kind of problem is, it's gonna use depth of search to branch out all possible solutions. Now some of these possible solutions, we're gonna find the answer that we need. But along the way when we branch out, we're gonna use bounding condition to stop the unnecessary branching for better performance. Let's have a look at the tree that we have on the right. We're gonna use depth of search to create this tree. For our first choice of queen placement, we're gonna have 4 possibilities for queen 1. And by the way, with our placement strategy, we're gonna assume every queen is already on a specific row. Queen 1 is on row 0, queen 2 is on row 1, Queen 3 is on row 2 and Queen 4 is on row 3. So what we're actually finding is just the column number of the queens. Back to our first queen placement, we have 4 choices For queen 1, it can be 0, 0, which is this cell, or 0, 1, 0, 2, 0, 3, which are 3 of these cells. So for queen 1 placement, we can put queen 1 in one of the 4 cells. And that's what we have here. For state number 2, we're gonna choose the position for queen number 2. Queen number 2 also have 4 possibilities. That is 4 cells of this row. So our tree gonna branch out like this. For one option of queen 1 placement, we're gonna have 4 options of queen 2 placement. They are here and they are here, and so on. So you start to get the idea that for queen 3, we can also have 4 possible positions for each of queen 2 placement. We're gonna also have 4 options for queen 3 for this node, and so on. And it's gonna be the same thing with queen 4. We're gonna also have 4 options for queen 4 for each option of queen 3 placement. If we continue to do that for all other nodes on the right, our tree is complete. Then we're gonna have a full tree with 4 to the power of 4 equal to 256 ways to set up 4 queens. Now imagine we have this tree with all nodes branched out from root to leaf of 4 levels. If we do a depth first search, from the root node to the leaf, each node collection of a depth first search. For example, this one here, queen 1 0 0, queen 2 1 0, queen 3 2 0, and queen 4 3 0. This depth first search collection is one of 256 ways to put the 4 queens on the board. So if we do a depth first search for the whole tree, we have all possible ways to set up 4 queens on the board. That is the first part of backtracking. We use depth first search to branch out all possible solutions. Now for the second part. With bounding condition, we're gonna stop unnecessary branching for better performance. And the bounding conditions are very simple conditions. Usually they are the conditions that are already given from the Roblin statement, which are this condition we have here. The queens cannot attack each other. They cannot be on the same road, they cannot be on the same column, and they cannot be on the same diagonal. So we're gonna see how bounding condition helps to improve the performance of backtracking. Let's say that we start from queen 1 0 0 position. From this position, we're gonna have 4 options for queen 2 placement, but because of the bounding condition, we cannot choose 1 0, which is this cell here, because the queen cannot be on the same column. So this node is bounded, and stopping at this node means that any branching after this node will not happen. And as you can see, we can skip a lot of branchings and node visiting because we have stopped here. Next, we look at the second option for queen 2, cell 1 1, which is this cell here. We cannot place queen 2 there neither because of the bounding condition say that the queen cannot be on the same diagonal. So for our branching, queen 2 placement at 1 1 is not an option anymore, and we stop the branching here, and that is removing a lot of nodes. So by now you should get the idea that after having new queen placement, we're gonna check bounding conditions to see if we should stop the branching or not. And these bounding conditions actually helps a lot in improving the performance of backtracking. Because you can see here, with only one queen placement, we already eliminate more than half of the cell where we can place a new queen. And with the second queen placement, we only have 2 cells left. So with the bounding condition, the tree stops branching really fast. And that is how bounding conditions helps to bring the time complexity of backtracking down to usually polynomial time, which is a really good performance for a brute force solution. And solving a problem like this, listing out all possible choices and eliminating unnecessary branching, is actually the true power of computer in solving problems. Because there's a lot of problems that is very hard to solve logically, but then by applying backtracking, solving it become very easy, systematic, and it also have a decent time complexity. So this is a huge mindset switch for you as a software engineer. That is from solving the problem to providing a way to list all possible cases of the solution. The bounding is too obvious. It's already on the problem statement. Next, we're gonna have a look at backtracking iterative implementation with 4 queens. And this is our implementation. But I'm gonna do it step by step for you to easy to understand. And I'm gonna start with step 1. So in step 1, we're gonna use depth of search to list out all possibility, 256 possibility of queen setups. Because for each queen, we have 4 possible placement. And for that, we simply have 4 nested for loop. The first for loop is to choose queen 1 position. The second for loop is to choose queen 2 position. The third for loop is to choose queen 3 position. And the fourth for loop is to choose queen 4 position. And for each of the full setup, we're gonna push that setup into the result array. And then we're just gonna print it out. So state 4 is the final state where we have the position of all the queens. And their positions are like this. The first one is the queen number. For example, this is queen 1. The second one is the row. Queen 1 is always on row 0. And the third one is the column, which is from 0 to 3. That is for the first queen. And this is for the second queen, the third queen, and the fourth queen. So if we run our step 1, full branch out, this is what we're gonna get. All possible placement of the 4 queens. And if we want to check the length, it's gonna be 256 ways to set up 4 queens. Now if we look closely at the first few position, the first one here is actually the node collection of depth first search. For this depth, 0, 0, 1, 0, 2, 0, and 3, 0. It's a depth first search of node collection for this branch. And the second one, with the only difference is queen 4 position, is the node collection for this branch. 0, 0, 1, 0, 2, 0, and 3, 1, which is the first column for the first 3 rows, and the second column for the last row. So our step 1 is done. We have the full branch out. Now we're gonna make it performant. We're gonna have a function to check the bounding condition. The input is the current node collection of the depth first search, which is basically whatever nodes the depth first search has collected. And it's gonna return true or false to stop the branching or to continue to branch. So in step 2, we're gonna kill the branch with the bounding conditions. This line here in step 2a is simply prepare the data to check for the bounding conditions. This line here for 2b is simply apply the condition to kill the branch. So if the queen in the same diagonal or the queen in on the same column, we're gonna kill this branch. And we return true to stop the branching. Otherwise, we're gonna return false to continue to branch. So we're gonna copy this one and put it here in our development. Next, we're gonna apply the bounding condition to stop the branching. And this is how we do it. For each of the new state, we check if it's a bound. If yes, we stop the branching. And we're gonna do this for every new queen placement. This is the placement of queen 2. This is the placement of queen 3. And this is after the placement of queen 4. And then we are done. So if we run our algorithm, these 2 are the successful setups of the 4 queens that satisfy the conditions that they're not gonna attack each other. For example, this line right here is this branching that we have in the green. It kills a lot of branches, and we can see here. And finally, it gets to a solution like this setup where the queens do not attack each other. In real life, if your data set is big, you can try your branch out algorithm with a smaller set of queens first. For example, we can start with 1 queen or 2 queens to see if the final state of the branching is correct. And then we can apply it for a bigger data set. For example, for n queens, 100 queens or something. So that is how we do backtracking. We do step 1, full branch out, and we apply step 2, bounding condition.